An LNG vessel full of more than 100,000 cubic meters of liquefied natural gas makes its way to a terminal. The U.S. Coast Guard has specifically authorized this delivery and maintains a safety and security zone around the tanker. No other vessels are allowed to enter this zone. Once the ship is docked, the liquefied gas will be pumped to a marine terminal that will gasify the liquid product and send the natural gas out into a network of pipelines. To some, the movement of this amount of fuel into a harbor looks like a very hazardous undertaking. Yet 3 decades of experience with LNG shipping have demonstrated that the risks can be managed. This program is titled Liquefied Natural Gas. It is designed for fire marshals, fire chiefs, government officials, and other personnel who may be responsible for planning, coordinating, or commanding an emergency response to an LNG incident, or who may contribute professional opinions about the possible siting of an LNG facility. This new power plant burns natural gas in a turbine similar to an airplane's jet engine. In the initial stage, energy in the gas is converted directly to mechanical and then electrical energy, with no need to use steam. However, the exhaust gases are still hot enough to generate the steam necessary to drive a conventional steam turbine downstream. This combined cycle process results in an efficiency of 50 to 60%. As much as 60% of the energy in the gas is converted to electricity. Conventional steam generation has an efficiency of about 35%. Natural gas is the cleanest burning fossil fuel. Natural gas produces less of the greenhouse gas carbon dioxide and less of the pollutant sulfur dioxide than coal to produce the same amount of heat measured in BTUs. Because of these advantages, more new power plants are designed to burn natural gas. Many motor vehicles now use natural gas in order to reduce emissions. At first glance, the United States appears to have an ample supply of natural gas. Annual production is projected to expand to 29 trillion cubic feet by 2020. However, demand is projected to increase to 34 trillion cubic feet by 2020, a shortfall of 5 trillion cubic feet a year. There are huge natural gas reserves in other countries, but the challenge is how to get this gas into the U.S. pipeline system. Natural gas is composed primarily of methane. It is a flammable gas similar to propane, except that while propane is heavier than air, natural gas is lighter than air. Natural gas is non-toxic, although it can be an asphyxiant if it displaces oxygen in a confined space. Natural gas is colorless, and in its natural state, odorless. An odor it is added as a safety feature before distribution to homes and businesses. When cooled to 260 degrees below zero Fahrenheit at atmospheric pressure, natural gas turns into a liquid. Liquefied natural gas occupies 1/600th the volume of the material in its gaseous state at normal atmospheric pressure and room temperature. Thus, liquefying the gas provides a practical and economical method for transportation and storage. Because LNG exists at extremely low temperatures, it is considered a cryogenic liquid, hazardous in unconfined conditions because of its extreme cold. Contact with a cryogenic can cause severe damage to the skin and make ordinary materials subject to embrittlement and fracture. Cryogenic operations require specialized containers and piping. LNG is stored in containers made of metals such as 9% nickel steel or aluminum, and moved through stainless steel pipes that are capable of handling these low temperatures. LNG usually is stored and transported at very low pressures, typically less than 5 psig, in well-insulated containers. Heat, even ambient temperature, causes the liquid to boil, which helps maintain the LNG in its liquid state, a phenomenon known as auto-refrigeration. LNG may be transported by cargo tank trucks, designed like those used to transport liquid nitrogen and liquid oxygen. an insulated tank that acts like a big thermos bottle. During transfer operations, the piping is cold enough to condense moisture from the air, forming visible clouds. Workers wear heavy gloves to avoid freeze burns. At ambient temperature, when uncontained, LNG boils rapidly. If it is spilled on the ground, it will boil more slowly as the ground cools. If spilled on water, it will float and boil very rapidly. The resulting vapor cloud is very cold and quite visible because it condenses water out of the air. Initially, the vapor cloud is denser than air, hugs the ground and spreads laterally. As it disperses and mixes with air, the cloud becomes neutrally buoyant. It is important to remember that vapors may be present in ignitable concentrations outside the visible cloud. A natural gas cloud may ignite, but will not explode if it is not confined. Liquefied natural gas itself will not burn or explode. It must be vaporized and mixed with air in the right concentration to make combustion possible. Natural gas is flammable between its lower and upper flammable limits of 5% and 15% concentration in air at ambient temperature and pressure. Outside of this range, it will not ignite. This compares with gasoline, 1.4% to 7.6%, and propane, 2.1% to 9.5%. Large quantities of LNG are shipped from overseas in marine tankers. There are more than 150 of these vessels in operation. These ships are made in various sizes, but typical capacity is between 125,000 cubic meters and 150,000 cubic meters of product. 150,000 cubic meters of LNG will yield more than 3 billion cubic feet of natural gas. Two primary designs of LNG ships are currently in use. In one design, the liquefied gas is transported in insulated spherical aluminum tanks. Another design uses an internal membrane of a special cryogenic resistant material covered with a layer of primary insulation. Then a secondary membrane and secondary insulation. Both designs incorporate a double hull, with the inner hull functioning to support the storage tank structure. Since the liquid cools itself as it boils, a small amount of vented gas is used as fuel for the ship's propulsion and power systems. Any residual vapors are vented through a vent control system to prevent overpressurization. LNG tankers dock and unload at marine terminals, which may be onshore or offshore. The LNG is unloaded as a cryogenic liquid, pumped from the ship to the terminal tanks where it is stored at near atmospheric pressure. It takes about 12 to 24 hours to unload an LNG tanker. Most LNG incidents that have occurred are associated with the unloading process. The few that have occurred have been minor spills. Typically, these are handled by facility personnel and do not require a response from community emergency responders. At the terminal, the LNG is received and stored until it can be regasified and sent into the pipeline system. The liquid is always boiling off vapor, which can be re-liquefied or sent out to pipeline systems. The storage tanks are double-walled and can hold up to 160,000 cubic meters of product, about 42 million gallons. The facility usually will have foam and dry chemical emergency fire suppression systems to extinguish fires from small releases and prevent accident escalation. Tank dikes are designed to hold at least 100% of the tank's maximum capacity. In addition to containing a spill, they control the size of the spill's surface, thus reducing the rate at which the vapor cloud is generated. The natural gas pipeline network has more than 300,000 miles of transmission lines carrying gas at pressures ranging up to 2,000 psi. Along transmission lines, compressor stations are located about every 100 miles. At these stations, the gas is filtered or scrubbed and recompressed to be sent along the pipeline. There are 1.8 million miles of local distribution lines, delivering natural gas to customers. Over 100 peak shaving LNG facilities are located throughout the country. Their main function is storage, in order to make natural gas available in case of sudden surges in demand, for example, during unusually cold winter weather. At these facilities, the LNG in storage may be pressurized to facilitate quick transfer to regasification units. In the U.S., there has been only one major incident, and it occurred at one of the country's first LNG facilities. In Cleveland, Ohio in 1944, a storage tank failed. LNG spilled into the storm sewer. The confined gas then ignited, killing 128 and injuring more than 200. The circumstances that contributed to this disaster could not be repeated today. Due to wartime shortages, the tank was constructed with metal that was too brittle. The dike was too small to confine the spill. Lessons learned from this terrible accident were incorporated into extensive safety codes and standards which govern industry performance today. All major industrial operations involve some hazards and risk. It is important to remember that hazards are constants, whereas risks can change. When the hazards and risks are understood, they can be managed to protect workers and the public. What must authorities having jurisdiction and emergency responders understand to make sound decisions about risk management? How do the hazards and risks of LNG compare to others more readily understood? There are potential hazards in our homes. There are construction materials that are flammable, flammable gases, heating fuels that are combustible, batteries that might explode at high temperature. Our own behavior can increase the risk of fire, leaving burning candles unattended, smoking in bed, or storing flammable liquids in the basement. Then there are risks over which we have no control, a lightning strike, or becoming the target of an arsonist. Yet we are secure living in our homes because society has learned to deal with the hazards through risk management. Good electrical codes assure that the likelihood of an electrical fire igniting in the walls is very low. Construction codes prohibit the use of easily ignitable materials. Heating systems are designed to be leak-proof and to shut down if a malfunction occurs. Even though house fires are uncommon, we are prepared to deal with them. Most homes have smoke detectors that warn people if a fire starts. Most people know the rules for escaping from a fire.
What's that?
Smoke detector.
Go get the baby.
Firefighters are trained in rescue and fire suppression. The overall risk is the sum of all the potential risks. The smaller risks are usually more likely than the extreme risks, and all risks may be reduced by more careful behavior.
Here are all the lines, then we hook up to it. We have 4 unload arms and 1 vapor arm.
The same general approach is used for managing the higher risks associated with large-scale industrial operations involving potentially dangerous hazardous materials. To understand the risk, certain questions must be answered. What hazards are present? What is the history of failures and what have we learned from them? How might failures occur? What is the likelihood of such failures? What are the consequences of each scenario? Then, a plan must be made to respond to each scenario. Overall, the risk needs to be low enough to satisfy regulators, insurers, workers, and neighbors that the operation is acceptably safe. The hazards of LNG are constants, the known properties of the fuel. LNG is a cryogenic liquid, and its vapors are a flammable gas. What failures might occur? Equipment failure could result in a liquid or vapor release, and a fire at the point of release. A dispersing vapor cloud from a spill could reach a source of ignition and burn back. A release into a confined space might result in an explosion. LNG vapors could displace oxygen and result in asphyxiation. A tank truck could be involved in a collision. Sudden remixing of strata in a tank could result in rapid vaporization and tank venting. A release on water could cause rapid vaporization and bubble-like explosions, what is called rapid phase transition, or RPT. RPT has been demonstrated in the laboratory and in field tests, but has never been experienced in actual operations. Failures might result from natural disasters, like an earthquake or lightning, issues addressed in the stringent engineering design codes. History has shown that the likelihood of a major incident is small. LNG facilities have extensive hazard detection and control systems in place, including gas detectors, leak detectors, radiant heat detectors, smoke detectors, low and high temperature detectors, emergency shutdown systems, and fire suppression systems. Facilities also have extensive security and emergency response systems in place. All newer LNG facilities have exclusion zones, areas surrounding the facility where the operator or governmental body legally controls all activity. Exclusion zones are determined in accordance with U.S. Department of Transportation's regulation under 49 CFR 193. If there were to be a fire, heat levels in thermal radiation exclusion zones will allow an exposed individual time to escape without receiving significant injury. Certain land uses such as residences, schools, or healthcare facilities are prohibited or restricted within the exclusion zones. A facility may also have a flammable vapor dispersion exclusion zone. In the event of a release, vapor concentration at the edge of the zone will be below the lower flammable limit. Exclusion zones may differ depending on the hazard model used and the installation year of the facility. In addition, some facilities may be grandfathered. Demanding regulations and standards for design and construction reduce the risk of a catastrophic LNG accident. All LNG storage facilities must comply with federal safety standards. 49 CFR 193, liquefied natural gas facilities, federal safety standards. 33 CFR 127, waterfront facilities handling liquefied natural gas and liquefied hazardous gas, and with NFPA 59A, standard for the production, storage, and handling of liquefied natural gas. Personnel are highly trained. There are strict security measures and regular and thorough inspection of facilities. What are the consequences of something going wrong? A number of factors must be considered. What quantity is released? What is the location of the release? Is the release confined? What is the weather and time of day? What is the nearby population density? What exposures are threatened? What are the capabilities of response personnel? Once the hazards and risks are understood, plans can be developed for emergency response. First responders always conduct a form of risk assessment when they arrive on the scene and size up an incident. This kind of risk assessment is based on the responders' knowledge of the facility, their previous experience, and their estimate of what's going on and how the situation may develop. These assessments benefit from knowledge gained during pre-incident planning visits. For example, that high expansion foam and dry chemical are the best control and extinguishing agents for natural gas leaks and fires, and that water is best used for exposure protection, since water applied to an LNG fire will only intensify the burning. When planning a new or expanded LNG facility, engineers perform a different kind of risk assessment. The hazards are assessed. Then a mathematical probability is assigned to each risk, based on such things as accident rates and history of mechanical failures. Then a worst-case assessment is made. Usually the probability of such an event is low. Then this information is used to apply for permits, to design the facility and its safety systems, and to develop a risk management plan. In over 45 years of LNG shipping, covering more than 60,000 trips and over 90 million miles, there have been only a few major shipboard LNG incidents, none involving an LNG release. Therefore, there is no field experience available to help determine how a significant shipboard LNG incident might unfold. Potential failures in shipping may include collision, grounding, navigational error, mechanical failure, and spill during connection, unloading, or disconnection.
Yeah, the purpose of the discussion here is to talk about the LNG consequence analysis programs that we have here at Texas A&M.
Mathematical models exist for estimating the behavior and effects of spills and fires, but no model currently exists that takes into account the combination of a release of a cryogenic liquid through two ship hulls, its spread on the water's surface, vaporization, travel of vapor, and the likelihood of ignition. If not ignited as a result of the initial breaching of the hulls, approximations using existing models suggest that a rapid release could propagate vapor in the flammable range more than 2 miles from the point of release. It is likely that the vapor would find a source of ignition and burn back. There are 4 lines of defense for reducing the consequences of these risks. Well-designed engineering controls, frequently reviewed and updated standard operating procedures, trained and qualified operating personnel, and timely informed emergency response. Well-designed and engineered vessels reduce the probability of a release. Tankers are double-hulled as an added safety factor should the ship run aground or be involved in a collision. Vessels have several independent LNG tanks for additional safety. The ship has controls that shut down the gas system if it operates out of parameters. Fire protection systems include fire sensors, water spray, and extinguisher systems above decks, and inert gas for the cargo holds. Terminals have ship-to-shore emergency shutdown systems and may have quick-release couplings or other types of emergency breakaway systems to automatically disconnect transfer arms. Well-written, frequently reviewed standard operating procedures place controls on how vessels and facilities are operated. Vessel management plans for each port are developed by the U.S. Coast Guard captain of the port. The Coast Guard individually authorizes each arrival, creates and enforces safety and security zones around the vessel, and conducts a safety inspection of each vessel. The ships are guided into port by local pilots and maneuvered by harbor tugs. There are extensive safety and security provisions. Personnel who operate the facility and the vessels must undergo background checks, be well trained, and completely qualified. The officers and crew of an LNG vessel undergo extensive training in LNG safety and emergency response. Then, if an emergency does occur, the response must be timely, informed, and well coordinated. Fire officials and other emergency response organizations must work with plant management to develop a level of preparedness equal to the risks posed by the facility. They need to have a clear picture of what a credible worst-case incident would be, and a well-developed emergency plan for the facility and surrounding community that takes a strategic approach to emergency response. Emergency responders must have a strategy in place to quickly and effectively manage resources to meet incident priorities. The first priority is always life safety. The second priority is to stabilize the incident. The third priority is to minimize property damage. Depending on the incident, strategy may be offensive, an aggressive attack on the incident, defensive, concentrating on protection of life and property with less risk to response personnel, or when both offensive and defensive strategies pose unacceptable risks, non-intervention. The area is isolated and the incident is allowed to run its course. LNG facilities will have comprehensive emergency response plans which should be reviewed and understood by local emergency responders. In addition, these facilities are required by federal law to conduct emergency response drills on a regular schedule. Local and regional emergency responders should participate and critique the exercises to identify problems and improve response capability. An LNG incident may involve multiple agencies and jurisdictions, including the Coast Guard, state authorities, local emergency response organizations, and industry. Personnel from these diverse organizations must work as a team to mitigate the incident. In such cases, it will be necessary to establish Unified Command. Unified Command is a team representing key agencies that have statutory or jurisdictional responsibility for the incident. The team takes the place of a single incident commander, who normally manages routine incidents.
All the way up to the 16, we get traffic.
The challenge is to integrate the various response agencies into a single organizational structure, which is flexible enough to continually assess and modify incident objectives. Agencies who may respond due to statutory or jurisdictional requirements must make Unified Command part of their regular training and exercises. One concern is the risk of a terrorist attack. Tight security reduces the likelihood of a successful terrorist attack. Ships and terminal facilities are designed to withstand conventional major accidents, which also makes them very resistant to potential terrorist events. A Sandia National Laboratory study suggests that terrorist scenarios would not exceed other worst-case planning scenarios. Emergency planners have to prepare for a credible worst-case scenario, a massive breach of a container and the rapid release of all its contents, whether caused intentionally or by accident. They also have to plan for lesser accidents, where the possibility of escalation exists. Since the Cleveland accident in 1944, there have been no major releases of LNG. Onshore releases are contained within dikes designed specifically for the container. Releases from LNG vessels on open water are less predictable. Research studies have attempted to model the behavior of LNG spilled on open water. Modeling of an LNG spill in a harbor area is more difficult because of fixed and floating obstructions. Research continues. In general, the most significant impacts on public safety and property from a major spill exist within approximately 500 meters of the spill, with lower impacts at distances beyond approximately 1,600 meters from a spill, even for very large spills. For any new facility or proposed expansion, federal regulations require LNG operators to establish communication with safety and enforcement authorities in order to coordinate all facets of emergency response. The authority having jurisdiction must review the operator's engineering drawings and emergency response plans to verify that they are adequate to deal with a credible worst-case scenario. These worst-case risks are very improbable and do not contribute much to the total risk, but are of concern because of the potential for public impact. The authority may require additional systems or enhanced emergency response plans if it determines that the existing plans are inadequate. Natural gas is a clean-burning fuel that has the potential to meet a significant part of our country's future energy needs. To meet that need, large quantities of natural gas will be liquefied and transported. LNG is a cryogenic, which can vaporize to a flammable gas. Yet these hazards and the risks associated with transporting and siting LNG facilities can be managed by careful hazard and risk analysis, a combination of engineering, security, and safety standards, and a prepared and knowledgeable emergency response community.